we will start now the first poster pitches. So we have 4 short presentation of posters. So for the people who is registered, then you will be able to look to the poster and to talk with the speakers in the exhibition zone in AAAI. But now we would like to hear a short presentation from the speaker. So the first one is actually by Chris Harper, and the talk is towards an ontological framework for environment to the hazard analysis of autonomous.
Okay.
Do you want to share your screen?
I can share. I can share my screen. I think. Yeah. Hold on a sec. Right. Okay. Can you see that? I'll go into full screen mode. It's only 1 page, so.
Great. Yeah, we can see it.
There. Hopefully that makes it clear, because it's quite a. I put in quite an elaborate poster. Right. Okay. So yes. So this topic is a little bit peripheral to the normal run of kind of machine learning work. So my thanks to the committee for allowing me the chance to present a poster on this. It really reflects a topic that we've been developing at Bristol Robotics Lab over the last few years. Several years ago, we actually started to try looking at system engineering methods for looking at for assessing autonomous system problems. And in particular, we were looking at hazard and how we wanted to try and do hazard analysis on autonomy problems such as robot waiters or mobile assistant robots and things like that. In doing that, we actually found that there seemed to be something of a gap in the way the methods, the kind of conventional functional hazard analysis methods worked for autonomy problems, because they tended to focus very heavily on the kind of design mission of the robot and the intended agents or actors in the environment that the robot was designed to interact with. But they tended not to focus very heavily on all the other things that a robot, or certainly an autonomous system, has to deal with in the environment that are not related to its mission, but are there in the environment, and therefore the robot needs to interact with them in order to survive in the periods where it's not performing its mission. And there are hazards associated with all of these features. But the methodologies that were the conventional methodologies don't really help you in trying to identify all that. Now, it doesn't stop an imaginative, creative individual from identifying these things, but we were looking to try and improve the methodology so that it had more, it provided more support for doing this. We've been looking at ontology as a way of trying to provide a knowledge representation model to underpin this analysis and provide more information and provide stronger assurance that the methodology is complete and consistent as far as we can make it. It's going to be difficult to do that in for completely, but at the very least we can identify any areas of incompleteness so that we have an understanding of where safety requirements and hazards may have been overlooked. And at least then we've got some idea about the limitations of the safety analysis of the system. So what we're doing is trying to develop, and this is the current work, a large kind of ontological knowledge representation framework. The general kind of look and feel of it is presented in the panel on the right-hand side, and we are trying to, and that will then support the identification of features in the environment, which you can see. And so on the bottom end of the right-hand panel, the information model should link to analysis of an environmental scene, and hopefully try to improve our confidence and our assurance that we have as complete a safety analysis as we can reasonably achieve. We're looking at applications, particularly in driverless vehicles and assistive robots in healthcare, which is the project that supported this work at the present time. So we're looking at, and in particular, where this work connects to machine learning is it can be used as a way of generating scenario-based simulation testing. It can be used as a way of analyzing operational design domains for features that need to be built into the functionality of the system. And actually what recently we've been looking at, or certainly having seen some of the tutorials in this conference, we're going to start looking at explainable AI technology.
Summarize.
Yeah, I think we've done.
Yeah.
Yeah. So please check out the poster, the paper in the program, and I'll be in the poster session afterwards.
Okay, thank you, Chris. Yes, this is a very important point. All the poster has an associated paper. You can see the proceedings, but also you are able to join the exhibition poster to ask directly to the speakers. So next one is by Adrian. You can present.
Yeah, it's okay. You see the poster?
Yes.
Yeah,
it is so, overestimation,
yeah,
with guarantees. Go ahead.
Yeah, this is this one. So thank you for letting me present my work. So I'm Adrien Gaufrio. I'm working in Airbus, but I'm seconded in hÉigeartaigh Saint-Exupéry in the DEAL project. So the idea of the work is to embed neural network inside a critical software, and we would like, even if the neural network is very small, to have some guarantees on the network. In our experiment, in fact, the guarantees that we would like is to always, whatever the input point is, to always overestimate the reference function. So because why we want to do that, it's because if you, for example, underestimate the function, you can be at risk and have a catastrophic impact on the outputs. For example, if you underestimate the braking distance for a vehicle, you will hit the vehicle that is behind in front of you, or you can also run without any maintenance action. If you underestimate, you will have an issue. So this is the idea. So we would like this property, this is the form, for all X in the domain, to have the neural network that is the output of the neural network that is always overestimate the real output of the function. And this is for all any point, and we do not want to have a massive testing to demonstrate it. So how to do that? The first point is we have to create a measuring point. So in fact, for each area in the data, we would like to create a point that is always higher than the point inside the domain. And the second, so we developed several algorithms to do that. We developed a grid measuring point. We developed also a way with a function. And also, when you do not know the function, you only have data, an algorithm that is able to create measuring points with the data. So this is the first step to create this measuring point data set. The second step is to train the network. And in fact, we would like to, for each training point, to overestimate the training point. And for that, a sufficient constitution is to have what we call an increasing neural network. So when you have an activation function, it has to be increasing, and you have also to have all the weights that are non-negative. How to train such a network? We have to use asymmetric loss functions. So when you go to in the loss function, you want to more penalize an underestimation than an overestimation. So by using this kind of loss function, you will able to always train your network with a positive error and a non-negative error. And the second one is to have all weights that are positive, to have an increasing neural network. And the way is to project all the weights to the zero at the end of the epoch. So with that, we are able to formally guarantee the safety. we have able to formally guarantee the safety of the system. We have able to avoid the costly massive testing with guarantees, but the cons is that it's not scalable to the dimension. Thanks. Don't hesitate to see me.
Okay, thank you, Adrian. So the next one is by Franz Watawa. Are you there on the use of available testing methods for verification and validation?
Yeah, hello.
Hello.
One moment. Should work. So good. I hope you can see my presentation. Okay, that's fine. Good. So that was too fast. Okay, so thank you very much for the short introduction. I try to keep it as short as possible. Some more information you can find, of course, in my poster and in the paper, I have to say. So we are focusing on verification and validation of systems as a whole. So therefore, I enjoyed really the keynote of today in the morning. Because we strongly think that focusing on systems and assuring that the systems are doing right is very much important. I have been involved also on projects on certification and homologation in the automated and autonomous driving domain. The poster is about more or less discussing how verification and validation can be done. It comprises a lot of examples where we have done some work as well as others, of course. The problem with what we face basically is that a system comprises today not only the hardware, but a huge software stack that is involved, and focusing only on some parts may not be sufficient here. So we have to consider basically all the different actions and interactions of the system with the environment. So we have been focusing a lot of this detection of critical inputs, using also ontologies for this purpose. So at the poster, we can talk about, let's say, some solutions we have provided. So this the sequence of images you can see is a test case generated from an ontology about the environment in case where we tested an emergency braking system for cars. Unfortunately leading not to the desired interaction, even in the case that, let's say, the sensors were doing right, but in combination with the rest, it was not working. So if you're interested in, let's say, this part, this system verification and validation, please join my poster. And if you have some ideas, I'm happy to discuss this with you. So thanks a lot. And yeah,
thank you, friends. So the last one for this session is by Vibhu Gautam, runtime decision making and under uncertainty autonomous vehicles. You there? I think I'm not sure. Vibhu, yeah.
Hello. Let me know if you guys can see my screen.
Yes, very well.
Hello, thanks everyone. So in a quick short discussion about my work. So we try to do a safe decision making in autonomous vehicles, specifically at level 3 and level 4. So we had not been targeting level 5. And we found in level 3 and level 4, we primarily use state machine models for various maneuvers. The challenge had been all these, when we are deploying state machine, the challenge was how do we handle uncertainties? And specifically, if we are using a downstream process like CNN or something like object detection models. So what we did, we used a Bayesian approach for convolutional neural networks, which was used to detect the speed signs, and we also computed data and model uncertainty. So using both of these uncertainty, then we used a generic decision framework using Bayesian networks. So so it was more of a system level safety design which was also able to encapsulate the uncertainty coming from neural networks. So what we can see on the state machine figure and the table above, we have defined various states. These states were based on various assumptions using a platooning case study, which was an existing case study, and we defined 5 different states. So last one, the safest state was switching to ACC mode, so switching to a manual mode. And when we simulated this using a Bayesian network, we found that we are able to easily switch between the safe state and the unsafe states. Here, the prior values were handcrafted and were not learned from the data. Reason being, we didn't have that edge case data, which would be the next step. And yeah, I think that's it. If you have anything related to, if you want to discuss anything related to this work, please come over to my poster. Thanks.
Okay, thank you very much. I would like to invite to, we are now in a break.